So let's say we wanted to find the fundamental trigonometric limit, which is the limit as x approaches 0 of sine of x over x. If we plug in x equals 0 to the expression, sine of 0 is equal to 0, and the denominator becomes 0, so we have the 0 over 0 in determinate form, which means we can use L'Hopital's rule. So this means the limit is equal to the limit as x approaches 0 of d by dx of sine of x over d by dx of x, which equals the limit as x approaches 0 of cosine x over 1. If we plug in 0 into this new limit, cosine of 0 equals 1, so the limit is just equal to 1 over 1, which equals 1. So the limit is just equal to 1, right? But you might ask, isn't there a geometric proof for this limit? Why do we even need that when we can just use L'Hopital's rule like we did here? Isn't what we did so much easier? The problem with this is that you have to consider what we were really doing when we applied L'Hopital's rule. We were taking the derivative of sine of x when we took the derivative of the numerator of the fraction with the indeterminate form. And we were assuming that we knew that the derivative of sine of x is cosine of x. But how do we even know that to begin with? To find the derivative of sine of x, we would need to use the limit definition of the derivative. Let's see what happens when we try to find the derivative of sine of x using the limit definition of the derivative. So recall that the limit definition of the derivative is d by dx of f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. If we apply this definition to sine of x, then the derivative of sine of x is equal to the limit as h approaches 0 of sine of x plus h minus sine of x all over h. We should deal with the sine of x plus h term by expanding it using the compound angle identity for sine. If we use the compound angle identity on the sine of x plus h term, it becomes sine x cosine h plus cosine x sine h, and the minus sine of x stays the same, and all of this is divided by h. We can split the fraction and rewrite this as the limit as h approaches 0 of sine x cosine h minus sine of x all over h plus cosine x sine h all over h. And what I've done is I've grouped sine x cosine h and negative sine of x from the numerator into the first fraction, and the cosine x sine h term in the second fraction. If we factor out sine of x from the first fraction, we end up with cosine h minus 1 over h times sine of x. And if we factor out cosine of x from the second fraction, we end up with sine of h over h times cosine of x. So the entire expression becomes the limit as h approaches 0 of cosine h minus 1 all over h times sine of x plus sine of h over h times cosine of x. In this new expression, sine of x and cosine of x are in terms of x, and the limit is in respect to h, so we can treat them as constants. We can see that in the limit, there's the sine of h over h term, which means we need to know the limit as h approaches 0 of sine of h over h in order to find this entire limit. So at the start, we were trying to find the limit as x approaches 0 of sine of x over x, and we tried using L'Hopital's rule to find it. But in doing so, we would need to know the derivative of sine of x, and in order to find the derivative of sine of x, we need to know the limit as h approaches 0 of sine of h over h, which is the same thing as the limit as x approaches 0 of sine of x over x, just with a different variable. So in order to find the limit as x approaches 0 of sine of x over x using L'Hopital's rule, we would need to know the same limit. Do you see the problem here? It's circular logic because in order to find the limit, we would already need to know the exact same limit to begin with. So no, we can't just use L'Hopital's rule. The fundamental trigonometric limit comes first, and it's what we need to know before we can even find the derivative of sine of x, not the other way around. So this is why you absolutely need the geometric proof for the fundamental trigonometric limit. Yeah, sorry, I guess it turns out that the lengthy proof with the 3 triangles was necessary after all. I already did a video on the geometric proof, and another video on the full proof where I used the limit definition of the derivative to find the derivative of sine of x. I'll link both videos in the description.